tell me, what was the definition of stability? Do you remember? We defined this concept of stability of a function. If you don't remember the definition, then you can tell me what was the idea for it. We were studying social choice theory, and then
so the idea was about robustness, like when bits are changed with small probability that the function changes on.
exactly, very nice. We defined something called a row correlated distribution, correct? And then we said, what is row correlated distribution? We pick x uniformly, and then y is changed from x slightly. If assume that rho is very, very small, then y is almost like x. Everywhere there is a very, very small probability that x could be switched to the xi could be flipped. Correct. This was called the row correlated distribution. And with this row correlated distribution, the stability rho of f was checking where does the value of fy change very soon if we change x from y, right? So over this row correlated distribution, what is the expected value of fx times fy? This is how we define stability rho. Here, important point to consider, the probability distribution is not the uniform distribution. Generally, we have taken probability and expectation over uniform distribution. Here, the probability is over this row correlated distribution. This was, and we kind of did some exercise to figure out what it means. Remember, what was the probability of flipping?
1 minus 2 by 2.
The probability of flipping was 1 plus rho, correct?
No, 1 minus rho, because flipping is small.
Oh, right. No flipping is 1 plus rho by 2, and 1 minus rho by 2. This is the way we defined it, and then we wanted to get a Fourier expansion for this quantity, as we have done for other quantities. We want to come up with a Fourier expression first. The first step in that was to calculate the stability of simplest functions, which are parity. So I should not say f, but and do you remember what we got?
Root power cardinality of s.
Great. Root the power cardinality of s. And if you remember the discussion from last time, this is not enough to tell me the stability of rho of a general function. For that, I want to calculate even this. For two arbitrary subsets S and T, what is this value? Again, when I don't write the subscript of expectation, that means I'm picking my x and y from this row correlated distribution. This is the distribution at this point of time. Whenever it is not mentioned, default distribution is the row correlated distribution. Great. Then how do we figure out this value? Remember how we did it for chi-s? Now, what should we do for this? I'm waiting for ideas from your side.
We should try to find out the stability of the cross product terms, the terms of the form chi-sx times chi-ty.
What is chi-sx times chi-ty? Can we break it down? What sorry?
So for chi s intersection t, it would be chi s intersection t of x, y.
Correct.
And other than that, it would be just either x or just y.
Very. Sometimes I will get xi in the, for some indices, I will get xi. For some indices, I will get xi yi. And for some indices, I will get just one. And if you want to notice, you can actually clearly say which ones go with. If something is in S but not in T, then there will be just xi. If something is in T but not in S, there will only be yi. And if something is in intersection, then I will get both xi. And if something is not in S, not in T, it will not appear. This is very, right? And now you should be able to see what we want. Remember what we did for expectation of chi sx, not expectation of chi sx, but stability of chi sx. What property did we use?
Basically, that each of the bits are, independent of each other.
Correct. So xi's are independent over I. That means if I look at x1 and x2, they are expected, they are independent. I pick x1 separately and then x2 separately. There is no relation between them. That means the expectation will get expectation of,
Multiply.
yes, expectation will get multiplied. When events are independent, their expectation gets multiplied. This leads to and actually I don't even have to write the product symbol inside the expectation. I can even take it outside. This can move. This I won't change, it doesn't matter. This can again also move. The product can go outside instead of inside the expectation. And then what do I know about expectation of xi?
Zero.
X.
Sorry,
Expectation of xi is zero.
right? Expectation of y,
Zero.
0. Right? That means if s minus t or t minus s is non-empty, then this is going to be what is the other way to say this? That s minus t or t minus s is not empty?
S and T are different.
Exactly. This is saying s is not. This makes our life very simple. Now we can calculate the stability of an arbitrary function. The two things we will remember is expectation of chi sx, chi ty, if s is not equal to t, is 0, and expectation of stability of chi s is root to the power cardinality. Then we just apply my favorite theorem. What is my favorite theorem? No one wants to take a guess.
Linearity of expectation.
Yes, very good. If I apply linearity of expectation, this term will go to, or let me just write it in terms of I should say, what happens to the second? What do you think? Come on, you answer it. We can go quickly. We
This
can-
goes to 0.
right. This is going to 0 because f at s and f at tr, f at s and f at tr.
No, it's because your expectation of chi sx times chi dy is 0.
Right. F at s and
Oh,
f at
f at d are constant.
constant. So we can take them out. Once we take them out, then we have the thing which we just noticed that was 0. Great. And now what is this quantity? Chi sx, chi sy.
Chi s of xy.
That is okay. Will that help?
Rho mod s.
Yeah.
Rho
Why is
mod.
it rho mod s? Because this is stability of chi s. Correct. This gives us the formula for stability. Again, we were able to write some property of the function in terms of Fourier coefficients. It has a very, very nice expression in terms of Fourier coefficients. Like influence, we can also define stability. Any questions about this proof? Good. Now, you might have a question. Why did we do it? Any guesses? Anyone remembers from last time? How are you going to use it? We are going to prove what we call Arrow's theorem from this. This is one of the fundamental theorems coming from social choice theory. And it is going to have a very, very nice intuitive idea of what we are going to do. It is not a very abstract theorem which you will not be able to understand. It's a very nice theorem which has clear implication in the voting rules. Remember, we talked about Boolean functions, and we mentioned that if f is a Boolean function, it is a voting rule for n voters and how many candidates?
2 candidates.
2 candidates. Correct. Great. And then we saw in many ways that majority was the optimal choice. Suppose I change the problem slightly. I say instead of 2 candidates, I have 3 candidates. Now, how can you extend your voting? Can you use the previous voting rules, like or using Boolean functions? Can you define an election for 3 candidates? What would be the obvious choice? What would be the natural way to define an election? Since the atmosphere is very politically charged, I will take the 3 candidates to be A, B, and C. Okay. And I want to decide you have n voters. Let's say voter 1, voter 2, up to voter n. Each of them have their preference. Let's say V1 says, I will prefer A over B over C. V2 will say, I will prefer C over B over A. Bn will prefer B over A over C. Some preferences, right? How can I use these preferences to define an election between these 3 candidates?
there is a Boolean function for each candidate.
What do you there is how can you define a Boolean function for each candidate?
So, like a indicator function, 1 or 0 type.
No, but what are the inputs then?
Yeah. Um,
You are close, you are very close. It's not for every candidate. You can define a Boolean function for every
2 candidates.
pair of candidates, right? We can convert this problem into voting rule for n voters and 2 candidates. Let's do it this way. Let's define 3 elections. Now, voter 1 will give the preference. He prefers A over B. He prefers, sorry, A over B. He prefers C over B. And he prefers A over C. Okay. So you can make this, you can fill out this matrix. 1, -1, 1. Let's say 1, 1, 1. Okay. And then what will you do? You will apply Boolean function on the election A versus B. This will give me a winner of the election of A versus B. Let's call it f of x. Similarly, let's say, okay, I should say that this is x. This is this column is x. The next column is y, which is the votes for B compared with C, and then this gives me the answer f of y. Right. This will be the winner. I will apply the voting rule f to decide whether B wins or C wins, and then f set. Okay. Is this whether this election makes sense? That's a different thing. But is this idea okay? Is this way of doing election? Is this okay? Is something missing in this election, or everything is specified?
Sir, how you use this A over B as -1 and B over C as 1? How
You
do
can.
So what if all of these 3 are -1? So
Yes.
it would be like cyclic. A is preferred over B, B is preferred over C, C is preferred over A.
Right. But let me, first question is simple. See, I have just 2 options, right? Let's say -1 is that A is preferred over B, 1 is B is preferred. Or you can say that -1 means the first candidate wins in the election. 1 means the second.
Yeah.
Right. So that will define a rule. Is that okay, Anindya?
Yeah. And why this 1 1 1?
Yeah, exactly. So both the points which I wanted to make, you guys have pointed, right? Let me take Anindya's point first. It's simpler. Can any voter's preference, can any row be 1 1 1? Okay, let me just do the thing. Just make our task easier. Yes. So this is our strategy of election. It is not complete. Why is it not complete? Already Anindya pointed it out. Not Anindya, I think Aditya pointed it out, right? How will we decide the winner from fx, fy, and fz if all 3 were 1 1 1? Let's say I had got an answer 1 1 1 1 1. Then who is the other way to say it is in the input in a particular row? Can I have 1 1 1s or -1 -1s -1s?
Why is this the other way to say this? I mean, even without this, it could happen that fx and fy and fz are ones.
Yeah, that is true. That is true. But what I'm saying is the issue in these things is the same, that 1 1 1 or -1 -1 -1 is not a valid.
Yeah. It's not a valid like configuration for voting.
Right. It is not, I want to say it is not a valid ranking.
Yeah.
Correct. What we have done is the voters had a ranking. They did not have a string from -1, 1 to the q, right? Whenever you have three candidates, every voter will have a ranking, whether A greater than B greater than C or C greater than B greater than A, something like that. Correct. And then we converted it to a string of -1, 1 to the power 3. Correct. I need to hear yes, no. Is that okay? Should I explain it again?
Yes.
Yes, I should explain it again, or is it okay?
Is it? It's okay. It's okay.
It's okay, right? So we are converting a ranking into a string of length 3. Unfortunately, all of the strings of length 3 are not valid. There are 6 possible rankings, but there are 8 strings. And this is something which you have seen before. The 6 valid strings are the satisfying inputs of the function, not all equal. Do you remember this function? Where have you seen this?
First assignment.
In the sign, correct? So not all equal on 3 bits is 0 if and only if my input is 1, 1, 1 or -1, -1. You clearly see that 1, 1, 1 does not give rise to a valid, correct? 1, 1, 1 is saying I prefer A over B, B over C, C over. That a voter is not allowed to give us, right? A voter can't say that he prefers A over B, B over C, and C over. That's already confusing. He can't decide between the 3 candidates. How can we decide? Right? That means every row should be one of the satisfying inputs of this function NA3. This is something we know now. Otherwise, there is no hope of deciding. We can have a condition that when I'm making this election, and if I look at any row, every row is a satisfying assignment of. Now, some of you might guess, if all the rows are elements of or are satisfying inputs of NA3, then probably your fx, fy, fz will also come as NA3. Is that correct or is that not correct?
It's not correct because we could just define f to be 1 for all inputs.
We can define f to be, okay, let's take f to be majority, right? Because if you take the very absurd voting rules, then you can obviously get into that. So I will take away that possibility.
So basically, tribes can work away. I mean, say supposing we have, 3K voters.
Mhm.
Yeah, the first K voters prefer A over B. The second K voters prefer B over C, and the third prefer C over A.
Okay. Okay.
Then, in any, if we consider A competing with B,
Hmm.
then it will, they will say that A is the winner, or similarly for all the 3 cases. So it will be a 1-1-1 rule.
So which f are you considering?
I'm considering tribes.
Okay. I don't know why you are considering tribes, but even if you consider just f as majority, right? Even that will give rise to a problem. Okay. Let's say I have 3 voters, V1, V2, V3, A, B, C. Sorry, I should say A with B, B with C, C with A. Let's say 1, 1, -1, -1, 1, 1, and 1 minus 1. Okay. These are all valid preferences,
Yeah.
right? And if I take majority, my answer is 1. It's basically saying that I have picked my voters in such a way so that, there is a symmetry, as you were trying to do, right? You had 3K voters and you said K of them would be A is preferred over B, then K voters is that B is preferred over C. I have just taken the preference so that A, B, and C are symmetric. Hence, clearly, no one should be able by an argument of symmetry. So this is an example where all voter preferences are valid. Correct? All three are valid voter preferences or valid rankings. But still, majority is not giving a good answer. Right? I talked about it last time also. That this time I'm going to show you that majority might not be the answer everywhere. For majority, we saw why majority should be the voting rule. This is one example where majority does not seem to be a very good measure. Okay. Let me define a term which will make it easier for me to describe Arrow's theorem. It is called Condorcet winner. What is the Condorcet winner? If fx, fy, fz give rise to a valid ranking, then the winner is called a Condorcet. This is another way to say that my result outcomes for pairwise election were nice. The three outcomes I observed, fx, fy, fz, they give rise to a valid. What we have seen now here is there exist.
Can you repeat what was the Condorcet winner?
So we say that there is a Condorcet winner if for certain inputs x, y, z, fx, fy, fz give rise to valid ranks. That means they are not 1, 1, 1 or -1, -1.
If for some inputs.
If for some input, there is a Condorcet. Yeah, we say that for that input, f will give a Condorcet. Right. So what we saw was that there exist valid inputs on which majority does not give a Condorcet. You agree? Condorcet was the name of a mathematician, by the way. Okay, this is what we have seen till now. Questions about the definition of Condorcet winner or the statement which I have written now, which we saw in the last slide. Is that confusing? I think it's a very natural voting rule, but if some definition is not clear, I can do. But
Condorcet winner is the function f.
No. Condorcet winner would be A, B, or C. But what we want to say that for certain inputs, is there a Condorcet winner or not? Condorcet winner is someone who is winning unanimously. Like he or she is winning against every other candidate. I guess that's a better way to define. Let me. A Condorcet winner is a candidate which wins against every other candidate in the pairwise. Okay. Is that okay? Now is the definition clear?
Yes.
This is what we want ideally. We want a voting rule F such that we always have a Condorcet. Right? Our input should be valid inputs. That means no row should have 1, 1, 1 or minus 1, minus 1, minus 1. Then we are looking for an F which always gives a counter set. By the way, what is a valid input? When I say a valid input, what do I mean by valid input? Let's say in this picture.
It's just saying that in each row, all the numbers are not.
Correct, correct. So every row is not all ones or not all minus ones. Given such a matrix with 3n entries, if no row is all ones or minus ones, I do the election pairwise, then there should be a counter set. This is what I am looking for. That would be a good F, correct? We will say that let's choose that F as a voting, and then we can even hold 3 candidate elections. Any doubt till now? We are all okay on the same page? Okay, since no one asked any question, I assume you are all on the same page. What Arrow's theorem tells us is that the only such F is, do you want to take a guess? Can you think of a trivial function which always gives a counter set winner? Sorry?
Dictator.
Yes, the only such F is actually dictator or
Negative of dictator.
Exactly, negation of
Negation.
except that you cannot have an F such that you always have a counter set. This is what Arrow's theorem says. So yes, majority is bad for 3 candidate elections, but the only good candidate is dictator. This is, in some sense, that's the how should I say it, message from Arrow's theorem. This one was proved in 1950 by Arrow. It was a bigger proof, but in 2002, Gil Kalai gave a Fourier analytic proof, and we are going to see a very, very simple proof of this statement, Arrow's theorem. This is basically with the concept of stability we have studied, and obviously what I'm teaching you is based on Ryan O'Donnell's book. This entire lecture of today, the content is borrowed from Ryan O'Donnell's book, which I have given as a reference for this course. Right? Let's take a look at this. The idea of the proof is very, very simple. We want to calculate the probability of Condorcet winner for F. Now, what should be the first question? When I say that I'm going to calculate this quantity, what is the first question?
How would we define it?
How do we define what?
When does a condensate minute exist?
Oh, that we have seen, right? If I give you F, and if I give you 3 and
The indicator function for the existence of condensate.
No, that's going to the next step. Before that, there is a more important question. before we make sense of this condensate
Distribution.
for exactly. The first question you should ask is what distribution? And do you want to guess?
All the valid inputs
Exactly. Very good. All the valid inputs uniformly over all.
uniform. Yes.
More than that, I will say that every row is picked uniformly over all valid inputs of NAE. Right? I have to define this probability. How am I defining? Again, remember, what is our input? Our input is this 3n sized matrix, right? These 3n entries. This is my input. And I want to define a distribution over that. And the distribution is natural. It is not the uniform distribution, but it's a distribution where every row is picked uniformly and independent. Though each of the row as we require should be from satisfying inputs of which function? Not all equal. Okay. Now I'm picking my inputs such that for every input, there might or might not be a condensate winner, but what we want is that for every valid input, there has to be a condensate winner. That means we want this probability to be equal to 1, right? So other way to frame Arrow's theorem would be that this probability is 1 if and only if f is a dictator or negation of the dictator. Correct? This is another way to show Arrow's theorem. We are going to capture this probability. We are going to figure out the probability of condensate winner for f, and whenever if that turns out to be 1, then our f is good, otherwise it is bad, and then we show that f is only good if it is a dictator or negation. Have I missed anything? Are we okay? The thing to remember is we want to calculate this probability where the distribution is special. The distribution is written. With this distribution and with this expression, we have a new way to tell what arrows. We want to figure out when is this probability 1.
So the total number of rows picked can be anything. Like
Let's fix an n. What we will show is let's say n is big, n should not be 1 or 2 or something. But if n is big, and then fix n for any n big enough, this probability will be 1 only if f is a dictator or negation.
So this distribution can be framed like from the pool of all satisfying inputs, we are picking n rows.
That's you are saying randomly.
Yeah, randomly. Yeah, randomly picking n rows
Yes.
out of a pool of inputs, satisfying inputs.
No. See, satisfying input is a 3n input thing, right? So picking a row does not make sense. You can have satisfying rows and you are picking uniformly from the list of satisfying. Each row is picked uniformly. But
if we fix a specific number of rows, n rows, so we have to pick n rows out of all satisfying input rows.
satisfying rows. Yes. Think of, instead of satisfying rows, think of them as valid satisfying inputs of NAE.
Yes. Okay.
Yeah. So I'm picking n rows. Each of the row is picked uniformly and independently from satisfying inputs of NA3. That means it is actually going to be one of these, right? 1, 1, minus 1, 1, minus 1, 1, minus 1, 1, 1, minus 1, minus 1, 1, minus 1, 1, minus 1, and 1, minus 1. Correct? These are the 6 inputs, 6 satisfying inputs. Every row is uniformly picked from one of these 6 rows. Sounds good? That input is clear now?
Okay.
Right.
Yeah.
And
So
then
it can be same also. That is not a problem.
the rows can be same, right? 2 voters can have same preference. Yes.
Yes. Yeah, makes sense. Yeah.
Yes. And then we want to calculate this probability of condensate. Now, so remember, I am not going to write the distribution, but now you know the distribution we are talking about. Okay, it is not the same as the one in the beginning of the class. That was this row correlated distribution. Now the distribution is different. Under that distribution, we want to calculate this problem. Now let's try to solve Udit's problem. How do you express this quantity, Condorcet winner for F? When will we have Condorcet winner for F?
So we can express it as NAE of FXFY upset.
Very good. So we have these XYZs chosen in a certain way, which I described on the last page. Under that probability distribution, I want to figure out if this is true. Okay. Remember, NAE3 has inputs from -1, 1 domain, but the output is a 0. It answers 1. If not all the 3 bits are equal, it answers 0 others. What should I change? What have I written wrong here?
Expectation.
Yes, thank you. The correct thing is expectation. Because NAE3 of fx, fy, fz will exactly is the indicator whether I got a Condorcet winner for f or not. Good. Okay, now you tell me, what should I do next? Something which you did in your past is going to help me a lot. Now you have to guess what you did in your past. You did some, as they would say in our mythology, right? You did some good karma before that is going to help us in solving this problem.
Expand it into
Expand
its
it
polynomial form.
in the Fourier representation. Very nice, right? You have already done it. You might not remember it.
I'm
That's
not,
okay.
I don't think it should be called the Fourier representation because the, okay, it is, sorry.
If the
It is.
input was 0, 1, then it would not be.
Yeah.
Right? Yeah. Then this quantity, again, you can trust me on this. I am a nice guy, but you can, if you want, you can go to the solutions and check. But this is the Fourier representation. When I say this is the Fourier representation, I wrote this expression, and the point here is that I know the Fourier expansion of NAE3 function. Can you tell me what is the Fourier expansion of NAE3 function? On 3 bits XYZ, it is? Go ahead.
3/4 minus 1/4 xy minus 1/4 yz minus 1/4 zx.
Very nice, right? And I have just taken this Fourier representation and applied my favorite theorem, linearity of expectation. That gives me the expression. If I can figure out this expression, then I can prove Arrow's theorem. First thing to realize in simplifying this expression is
X and Y are not independent.
that is correct. That is correct. I can't write it as expectation of fx times fy. But what do you think about these three quantities? They should all be
Equal because
equal.
yeah,
because
it's
the
a same
symmetric,
expression.
yes.
Yeah.
It is symmetric between the three three elections. That's why this thing should be the same. The only thing now we want to figure out is expectation of fx fy. But remember, this is a this is a distribution, different distribution than uniform. This is when we are picking x, y, z. Sorry, I'm picking this matrix such that every row is uniformly and independently picked from a satisfying input of NA3. Right? This, just remember it as equation 1. We will use it later. But now our task is to figure a simpler thing. Right? We want to figure this thing out. Now, let me tell you few things about this distribution, right? Let's call this distribution D, right? Where I pick every row uniformly and independently from the satisfying inputs of NAE3. This is a kind of a slightly technical point, so please pay attention. You want to be clear with the technical things which are coming out here. Every row is, yeah.
Just one thing here,
Mhm.
X and Y are columns, right?
X and Y are columns, yes.
Yeah. Okay.
The of that matrix, right? The distribution is over this matrix which has 3 columns. X is the first column, Y is the second column.
Yes.
Every row is uniformly picked from satisfying inputs of NA3. This is our distribution. Great. You want to figure out X and Y. Let's see few of the things which we know about this distribution. First thing is, what can I say about expectation of Xi?
Zero.
Yeah,
Zero.
right? You look at Xi, right? It is one of the 6 inputs. I have equal number of times. I have one equal number of times. I have a -1. I am picking uniformly. This has to be 0. What about these pairs XY for different I? They are distributed obviously independently. Correct? Do you
Yeah,
agree?
because we can choose Xi and Yi independently, and then Zi will get fixed accordingly.
No. That this is no. Xi and Yi are independent over I.
Oh,
That right? X and Y are not independent. Xi and Yi are not independent. But if I talk about this pair X1, Y1, this is not telling me anything about X2, Y2. This is
Yeah, yeah,
because
yeah.
each row is picked independently, right? Correct? Each row is getting picked independently. This is just following from that. What about expectation of Xi, Yi? I can show you the 6 inputs. Right? So what is the expectation of Xi, Yi?
-1/3.
Yes. That is not 0, right? There is some relation of Xi and Y. This you can convince yourself. You can just multiply and check. Okay. Think of it this way. There will be 2 inputs where like -1, -1, 1 and 1, 1, -1. This is when Xi and Yi will give you the same sign, but there are 4 inputs when they will give you the opposite sign. Correct? So just apply the expectation with probability 2/3. You will get 1. With probability 2/3. With probability 1/3. You will get 1, and with probability 2/3. You will get -1. Right? So if I look at all satisfying inputs, 2 inputs will give me 1. For them, Xi times Yi is going to be 1. Those are the inputs when -1, -1 and 1 and 1 are there. And there are going to be 4 inputs in the valid rows, which give me -1. Correct? So this is probability 1/3. This is probability 2/3. Let's calculate the expectation value. 1/3 into 1 plus 2/3 into -1. This will give me -1/3. Okay. Now, once we know this, what does this tell us? Does this remind you of something?
We can write Fourier expansion of fx f, and there we would have terms like xy, xi, y.
No, think about stability. Think about what things we defined for defining stability.
Stability is basically -1/3 correlated.
Yes, yes. These 3 things are in some sense pointing to the fact that Xi and Yi are -1/3 correlated. In other words, X and Y, since because of the second point, X and Y are -1/3 correlated. Now, this is a jump, I know, but if you are confused about this, after the class, go and look at the formulas of how we derived Fourier expansion for stability. You will see that mathematically we only use these things and nothing else. This Xi, Yi, the second point, was used when we wanted to break our expectation into 2 parts or multiple parts, just depending on the ith bit. This is why the second thing was used. When we wanted to make the expectation 0 of chi sx times chi ty, we used the first point. And then when we wanted to show that the stability of chi sx is equal to rho to the power cardinality of s, this is where I use this fact. This is basically when it is rho correlated, it is saying that this quantity is rho. Other way to say it is, since this is a row correlated distribution with -1/3, this expression is actually very, very simple. This is something which we know. What is this?
Summation over all s
Yeah,
minus
no,
1/3.
no, but in terms of stability, then I will.
Stability of -1/3 of f.
Very nice. Okay. It turns out that if I look at the satisfying inputs of NEA3, they can be thought of as -1/3 correlated. And this is because they satisfy these three things. Questions about this?
So can we generalize it to any NAEN?
See, for generalizing to any n, the only thing we need is that every row is independently picked, right?
Yes, and then we will calculate this third quantity and then we will get
No. Every row, we don't have to worry about the third quantity. See, what I'm saying is that suppose there was just one I, n was equal to 1. Then the second row is not important. I am picking xi with probability half if expectation of xi is 0, right? It can only take value 1 and -1. That means what is xi? I am picking xi uniformly.
Yes.
And then the last quantity will tell me that yi changes with, corresponding row correlated distribution. If there was just one row, then clearly the x and y would be just one elements. Instead of a vector, think of them as a scalar. In that case, they are definitely row correlated distribution. This follows from point number 1 and point number 2. Now you take n such things which are all independent. And that was the definition for row correlated distribution. Right? So having n voters hasn't changed anything. I do not concern myself with the third column. I'm just talking about the first two columns here. If I look at a particular row of the first column, or first and second column, right? So if I look at just this, and if I'm picking something at a uniform distribution from satisfying inputs, I know that these are -1/3 correlated. That follows because expectation of xi is 0, expectation of xi yi is -1/3. These are variables which only take value 1 and -1.
Yes. So
Right.
my question was in regard to if we increase the number of candidates. So if let's
If
say we
we
have 4
increase
candidates, then
yeah, that's a complicated question.
yeah, then
So,
it
but
will be like 4 C2 combinations, and then we have to look at NAE 4 C2.
yeah, but the point is that like the kind of thing we are proving, if it works for 3 candidates, then it will definitely work for 4 candidates, right? If you don't have a Condorcet winner for 3 candidates, you cannot have a Condorcet winner for 4 candidates, right?
Okay.
Right. So that's why we are not the only dimension which is increasing is the number of voters. If we have already shown that no Condorcet winner exists for 3 candidates, then 4 is not useful, right? But you are right that if you want to calculate some other properties, then we will have to do NAE 4C2 or something. That is correct. NEA 6, right?
Yeah. Okay. Got it. Yeah.
So this was the important point, that actually the distribution we came up with, or if we looked at the satisfying inputs of NEA3, they are row correlated with rho equal to -1/3. Now, remember this equation 1. This tells us that the quantity we were interested in probability of Condorcet winner for F.
Just one thing. So
Mhm.
even the like xi and yi will be -1/3 correlated even for NAE4, or we have to calculate it.
We have to calculate this.
Okay.
You don't mean NAE4, you mean NAE6. If there are 4 candidates, this will give rise to 6 elections, right?
Yeah, NAE6. Okay.
Yes. So you will have to check. I can't say that that would be the expectation of xi yi would be -1 by 2.
Okay.
I don't see it directly. You have to calculate, right?
Yes.
But now this you see, right? From 1, there were 3 terms. Each of the terms are stability -1 by 3 of f. I just combine them. This gives me this value. Sounds good? This is from 1. Okay, now our task is very, very simple. When is this probability 1? What will be the condition of on stability?
When stability -1 by 3 of f is -1 by 3.
Exactly. Do you agree with my solution here? This probability is 1 if and only if stability -1 by 3 of f is -1. Do you agree? You clearly see that if I pick it to be -1 by 3, then 3 and 3 will cancel and I will get 1. Okay? This is something which you can all do. The bigger question is, when is this probability, when is this stability going to be -1 by 3? And how are we going to decide that? We are going to use what are we going to use?
The Fourier expansion.
Yes, the Fourier expansion. I should say okay. So what do I know about stability of -1 by 3 of f? What is the minimum possible value of stability of -1 by 3 of f?
-1 by 3.
Yes, this is greater than equal to -1 by 3. Why?
Because one lower bound happens when all the mod s is odd, and the f at s squared is concentrated only in the odd sized s.
Correct. If f at s is concentrated on an even part, that will give me something positive. I can ignore them. That means my stability is greater than summation over s such that s is odd -1 by 3 to the cardinality s f at s square. Correct? This is definitely true because even cardinalities would only add into this thing, and now the maximum negative value will happen when cardinality of s is equal to. This proof is also showing us that equality holds if and only if when will this exactly be equal to -1 by 3?
When mod of f at s is greater than 0 only for odd sized s.
No.
When mod s is 1.
Yes. When all my Fourier weight is concentrated in the first level. What do I mean? I mean f at s is not equal to 0 if and only if f at s is not equal to 0 implies cardinality of s is equal to 1. Right? Otherwise, this could never be equal to -1 by 3. If s was even, I would get something added positive in -1 by 3. If s was odd, but cardinality of s was more than 1, then again, instead of -1 by 3, I will get a factor of -1 by 27.
So when we said that this inequality, that like the stability would be getting equal to -1 by 3, then we are ignoring the fact that the I mean the entire weight could be over the constant term.
No, if the
Could be
entire weight is
means
over
mod s could be 0 also for that.
no, if all the weight is on constant term, you will get something very higher than -1/3. You will get 1, right? This inequality is valid for any f at n, right? Yeah, that is so constant means you're talking about the even s, right? S is equal to pi. Cardinality of s is equal to 0.
Yes, that's also even.
That will also give you, yeah, addition in this term. So, yeah. So we got we can have a theorem which is almost Arrow's theorem, that probability Condorcet winner for f is equal to 1 if and only if all Fourier weight of f is on level 1. This is same as saying that f at s not equal to 0 implies cardinality of s is equal to. I only have Fourier coefficients non-zero at the first level, but this is something which we have done before, right? What are the Boolean functions for which the Fourier weight is considered only on level 1?
Basically the dictator functions, because we are talking about Boolean functions. I mean,
Exactly.
Yeah, dictator or negation of dictator.
Exactly. This is Arrow's theorem. By just analyzing the Fourier quantities, we were able to prove Arrow's theorem. This proof was again by Gil-Kalai. This was very recent in the sense that Arrow's theorem was proven in 1950, and then this proof came out in 2002, which was much simpler. And obviously, this exposition is from Randall's book.
So the theory of Boolean functions wasn't developed much back in the 1950s, right?